testbed called a smart conference room. The goal of smart lighting systems is to improve energy efficiency and human productivity, but we have to make sure that we make the light comfortable for human beings. Our approach to this is using the fusion of sources, in this case LED lights, sensors, and control algorithms. We also want to address control challenges such as energy efficiency, human health, etc. So the smart conference room is an adaptive lighting test bed, as I said before. It's also a regularly used conference room for presentations, meetings, etc. The room is equipped with 10 5-color channel fixtures. These are individually controlled, and independently controllable. There are also 53 RGB sensors that we use for our color sensing, and these are low power with a dynamic illuminance or lux measurement. We also have 18 time-of-flight sensors or distance sensors, and these are similar to the laser rangefinders you can get at the hardware store. Both the RGB sensors and the time-of-flight sensors are installed in the ceiling of the room and are installed in such a way that they give full coverage of the room. The entire systems level vision of the room can be summarized as follows. We have our room and our fixtures. To add to this, we have our sensing components, RGB, and occupancy. Based on just these, we can construct control algorithms. However, we don't believe this is the complete view because there are additional components such as user preferences, building specifications, ambient light coming in from outside, etc., that we also need to control. This overall system can be summarized into two main parts: the color sensing done by the RGB sensors and occupancy sensing done by the time-of-flight sensors. I'll begin by focusing on the RGB color sensors. Our plan can be modeled like this. We have our light field in the room, which is generated by a combination of our LED fixtures and our ambient lighting. This light field is sensed by our RGB sensors, or array of RGB sensors. Using this sense measurement and our desired values, we can minimize a cost function based on a set of optimization constraints. For example, we can make a cost function that balances the quality of the light and the energy efficiency of the system set to an optimization constraint such as the saturation of the light fixtures, for example. Here I will demonstrate the actual daylight harvesting that we're able to do using these RGB sensors. There are a few things I want to point out in this video. First of all, at the initial point, our total power consumption is about 213 watts. This graphical user interface shows the sensed input, the sensed light by all 53 sensors, and at the bottom, the power consumption of both the complete fixtures and the individual channel of these fixtures can also be seen. At the bottom is where we took this algorithm and we extended it to a day-long test. We started about 5 in the morning and ran it to about 8 p.m. The graph at the top is representative of the total power consumption of these fixtures. Total power consumption sensed by these sensors, and the bottom is the lux or illuminance measurement of these sensors. Interesting is like around noon where you see incoming daylight, the LED fixtures turn down to compensate for this incoming daylight, maintaining our set point requirements. And you can see there's also a spike in the illuminance that's sensed by the color sensors at this point. All right, with this, I'll move on to the occupancy sensing portion of the room. All right. Our occupancy sensing algorithm is based on the fact that in an emitted light source, the distance can be calculated as a function of the speed of light and the phase shift of a frequency modulated signal. Using this information, we can construct smart panels, essentially having these light rays emitted from the entire room, and with that we can get reasonable localization measurements, we can get pose estimation, we can get video frame rates. This operates in real time, and it's privacy preserving. In the right of this picture, we have, the right of this slide, we have the result from one of these sensors. Here you can see the z-axis shows the height of the room, and the x and y axes basically show the spatial coverage of the floor by the sensor. Here you can see there's someone sitting, but it maintains the privacy again, which is a major concern that we have. This is a demonstration of the algorithm. Here you can see as the occupants come into the room, we're able to detect them, give everyone a tag, and more importantly, we're able to get the relative position and height of all these occupants. With this information particularly, we can move on towards activity modeling in terms of, determine whether there's a PowerPoint presentation going on, has someone fallen, etc. The future work, we're going in multiple directions in this. They're exploring human factors. For example, we're currently moving the system, we're exporting this system to a hospital room at the University of New Mexico to do real-time evaluation on human subjects. And we're also developing more advanced pattern recognition algorithms to do this occupancy sensing. We're doing multi-sensor fusion of the time-of-flight sensors, moving towards single pixels of the multi-pixel view that we have, and combining this with the RGB color sensor data to maintain the level of occupancy sensing that we're able to do. We're also moving towards including building automation such as automatic shutters, communication with the HVAC system, etc., to make a more complete view of the smart conference room. And with that, I'll take any questions.